Good morning. So let us start on our description of the directed graphical model. We'll study three type of graphical models: a directed model, undirected model, and factor graph models. And also for each type of model, we'll study three tasks. One is a representation of a model in terms of a graph, and then inference in the model, which basically means finding out probabilities of certain variables, and then finally learning the or estimation of the parameters of the model. So let us start with the representation first. As we discussed before, that a directed graphical model is a representation of a factorization of a joint distribution. For example, if we take this joint distribution, you can factorize into this just by application of the chain rule. You can factorize into this. And note that this is not a unique factorization. You might as well have other factorizations. And you draw a graph to represent the factorization. Note that even though the factorization eventually represents a joint distribution, but the graph has a correspondence, one-to-one correspondence with a particular factorization. And there may be multiple factorizations of the same distribution. So this is how you represent the graph. For every variable, you have a node. So for every variable, you have a node in the graph. And it's like this. You look at that variable. For example, let us look at C. You know it is conditioned on B and A. So there will be a directed edge from A and B to C. A and B to C. So the rule is look at the factor where C is present, look at the node C, look at the conditions in that factor. So these are the conditions in that factor, and draw directed edges from the conditions, in this case A and B, to the node C. Similarly, this is another factor corresponding to B, and it is conditioned on A. So if we look at B, there will be a directed edge from A. PA it does not have any condition, so it has no incoming edges to it. You might notice one thing, that since this is a general factorization which holds for any arbitrary distribution, you basically have every node connected to everything else. And for special cases of distributions, you may have some of these edges in the graph missing. For example, if it was a independence assumption, naive based kind of thing. So if we had PA BC equal to PA times PB times, these are the factors, and then you would have a totally disjoint directed graph. Okay, so this graph will be, so every edge you drop, you put more and more restrictions. See, there is a correspondence between a factorization and the graph, but the factorization is for a distribution. So the particular type of factorizations which are given by a graph will correspond to more and more restricted distributions if we have less and less edges in the graph. And note that this is just a representation. This doesn't give any additional information about the distribution besides the factorization. It only is an information or a graphical representation of a factorization, nothing more, nothing less. So let's take an example of this. So there are 7 variables here, and I can write down the factorizations easily. So let's look at x1. X1 doesn't have any parent, so it will not have any conditional. X2 doesn't have any parent, it will not have any conditional. X3 doesn't have any parent, it will not have any conditional. Look at x4. X4 has 3 conditionals, so x4 into what are the 3 parents? X1, x2, and x3. So it will be conditioned on x1, x2, and x3. Look at x5. X5 has two parents, x1 and x3, so it is conditioned on x1 and x3. X6 has just one parent, x4, and x7 has two parents, x5 and x4. Okay, so this graph corresponds to this particular factorization of this joint distribution. A more sort of general way of writing this is that the joint distribution is factorized in terms of this product, where it is, if you have v vertices, you have v factors, and for the factor corresponding to the ith vertex, that is the ith variable, is xi, conditioned on given the parents of the ith vertices. So say I equal to 4, the factor would be px4 given the parents of 4, which is x1, x2, x3. Okay, so this is the meaning, this is the syntax. As it turns out that I previously said that this doesn't give any additional information, but it actually does. This factorization does represent something. It represents something called an influence. So it basically means that if there is an arrow from x3 to x4, it means x4. So if you have an arrow from x3 to x4, it means random variable x3 influences random variable x4. Okay, so this is a semantics. This is the meaning of this graph. The factorization is just a syntax, and this is now we are looking into what it means. What does the representation mean? So the first meaning we can talk of is kind of a causal relationship or an influence. I mean, I call it a causal relationship, but it's actually an influence. In certain cases, these two are same. It's an influence of one on the other if you have a direct edge. So let us concretize a little bit more what this influence means. See, okay, let's take this, or let's take this. What this influence means is that suppose x3 influences x4. So if you look at the probability of x4, you get certain values. Suppose I fix the values of x1, x2, x3, x5, x6, x7. You get some probability estimate of some probability value for x4 taking on certain value. Say x4 is binary, probability that x4 equal to 1, you get some value, say 0.6 or something. Now, suppose I observe x3. Suppose I observe x3. Okay, so that means I can tell you it's like this. So the probability it rains on a certain day is say 0.6 in Kharagpur. It rains on a certain day is 0.6. And let's say x3 is that there is a depression in the Bay of Bengal. So if we know that there is a depression in Bay of Bengal, the probability that it rains in Kharagpur actually increases. Or for example, if you know that there is no depression in Bay of Bengal, the probability that it rains in Kharagpur maybe decreases from the unobserved value. Let's say it decreases. Okay, so that means your kind of belief about x4 equal to 1 gets revised after observing the value of x3. This is for, or alternately, let's say, is it snowing in New York? Let's say that is x3. It is snowing in New York. Yeah, so even if you observe that it is snowing in New York, it doesn't change your probability of it's raining in Kharagpur. So in that case, it doesn't influence. So this we say, so if this happens, that this probability is revised to then we say X3 influences X4. That means knowledge about X3 would change your belief about X4. Knowledge about X3 would revise your belief about X4 happening. If that be so, then we call X3 influences X4. Note that the other way may happen also. So for example, suppose I know it's raining in Kharagpur. I know it's raining in Kharagpur. And what is the probability that there is a depression in Bay of Bengal? There is a depression in Bay of Bengal. That also, so in general, what is the probability of Bay of Bengal depression in Bay of Bengal? Let's say 0.2. But if we know it's raining in Kharagpur, maybe this will go up to 0.3. Okay, so it's the other way around. It's not just causal, it's evidential also. It's evidential also. So in this case, so this is X. So one thing is obvious that if there is a direct edge, of course there is an influence both way, in the direction of the arrow and in the reverse direction. So direction of the arrow would be called a causal influence. The reverse would be called an evidential influence. But there are indirect influences too. For example, X1, observing X1 not only changes your belief about X4, but also changes your belief about X6. So there is a flow of, there's a kind of flow of influence. There's a flow of influence. Okay, so there are long-range influences too. What the Bayesian network and some graph theoretic results tell us that you can actually, given a Bayesian network, by the way, this directed graphical model is sometimes called a Bayesian network. This directed graphical models helps you just looking at the graph, find out such long-range influences. Okay, so this is the formal definition. I have already given, I'm not given it. The point to be noted is that there is a one-to-one correspondence between a graph and a factorization. But there is no one-to-one correspondence between a graph and a joint distribution, because a joint distribution might have multiple possible factorizations. Okay, so there is one more part of the syntax that I missed, is that in addition to, so let's take here is a network. I'll briefly explain the network because I'll use it later. So there are 5 variables. The difficulty of a course. This is a famous example due to Daphne Koller. There is a difficulty of a course, which is a random variable. It changes from course to course. There is an intelligence of a student, which is also a random variable, which let's say difficulty is 1 or 0, difficult or not difficult. Intelligence is also smart or dumb, 2 values only. We call them I0 and I1. Similarly, difficulty we call D0 and D1, these 2 possible values. And there is a grade that you get in the student, that you get in the course, a particular student gets in the course. Grade has 3 possible values, let's say G1, G2, and G3. Okay, and the student also takes a GRE or a SAT or some kind of exam. And in the exam, the students can either do well or see. So the exam outcome also has 2 values, S0 and S1. And finally, the student gets a letter of recommendation from a particular professor. And the letter of recommendation again is good or bad, L0 or L1. And what type of letter the student gets, L0 or L1, depends on the grade she has received in the professor's course. Okay, so now you can see the direct influences. Direct influences are the grade in a particular course is affected by that, is directly influenced by the difficulty of the course as well as the intelligence of the student. the hard work is unmodeled here. The SAT score is also influenced by the intelligence of the student. The letter, the type of recommendation letter that the student gets is influenced by the grade, not directly by intelligence, by the grade the student gets. Now, we have already discussed about conditional probabilities. Now, for every node in this graph, I annotate or attach something called a CPD or conditional CPT, conditional probability table. So these are what are called conditional probability tables. Okay, so let's look at what these tables mean. Let's look at this table. Okay, so this table is grade G1, which can take three values G1, G2, G3. G, which can take three values G1, G2, G3. And it has two parents, difficulty D and intelligence I. And there can be four different possibility combinations of the parent. So I0, D0, I0, D1, I0, D. This will be I1, D0, and this will be I1, D1. Okay, so the parents, since they are binary, they can take four possible combination of values. And what this conditional probability tells is that, so this entry, for example, is the probability PG1 given I0, D0 is equal to 0.3. Okay, so this is the probability of the current variable taking on certain value given certain combination of the parents. Okay, so I could have also written this matrix as a table of say I, D, and G. So 8 different, no, not 8, 2 into 2 into 3, which is 12 different combinations of I, D, and G. I could have also written as a table where the final column would be these values 0.3, 0.4. But okay, this is a more compact, easy to understand representation. So this is this is the idea. So every entry of this CPD would be the particular value of that variable given a particular value conditioned on the particular value of the parent combination of the parent variable. So that is the table. Note one thing, that each row of the of this CPT adds to 1. You can see it. Each row of the CPT would add to 1, whereas the columns need not add to 1. The rows would add to 1. Okay, so the rows add to 1. So similarly, for every node, we will have this. The nodes which do not have a parent would be just their prior probabilities. So the prior probability that a course is difficult is 0.6, and the course is easy is 0.6, whereas the prior probability that course is difficult is 0.4. Okay, so this is the complete representation of a directed graphical model, sometimes called a Bayesian network. By the way, one more thing I forgot to mention in the structure, that this would be a directed acyclic graph. This would be a acyclic graph because of the nature of the, we'll see later, but because of the nature of the thing. Because if X3 influences X4, it's not that there is another cycle which would kind of recursive. There is no recursive influence. X3 influences X4 and X4 influences again X3 again. This kind of recursion or recursive causality. Influence is there. Influence can be recursive. Influence is bidirectional, but recursive causality is not there. So it's acyclic. It's sometimes called a DAG, a directed acyclic graph. Okay, so this is the complete representation, the DAG structure as well as the CPTs associated with each node. Why is this important? Because we can easily see that you can reconstruct the joint distribution. You can reconstruct the joint distribution using this DAG and the CPTs. How? Because we have already seen in the previous slides that this is a factorization. So every graph is a factorization. So what is the factorization? Product of Pxi given parents of xi. So these will be the terms. This will be the term. So for example, what is the representation here? If we look at difficulty, intelligence, grades, and SAT and letters, if we look at the graph, it would factorize into this from the graph structure. PD into Pi into Pg given I and D, the parents of G, Ps given I is the parent of S, PL given G is the parent of L. So this is the factorization. Now, if I want to find out, okay, if I want to find out, so suppose I want to complete this, completely write down this joint probability distribution. So what would it look like? It would look like something like this. So I have five values, D, I, G, S, and L, and this would be the corresponding probability. So D equal to D0, I equal to I0, G equal to G0, S equal to S0, L equal to L0, D equal to D1, I equal to I0, G0, S0, L0. So all these kind of, how many entries will be there? There will be how many? So 2 into 2 into 3 into 2, 2 into 2 into 3 into 2 into 2. So 4 to 8, 8 into 3, 24. 24 such, no, not 24. Okay, you can find out how many such entries will be there. Each of these are binary except the grade. Okay, so you can find out 2 to the power 4 into 3. 2 to the power 4 into 3. So many entries will be there. And how do I find out the probabilities for the complete description? How do I find out the probabilities? You look at a particular thing. So say I want to find out the probability, joint probability of P, D0, I0, G0, S0, L0. So what is the probability that course is easy, the student is dumb, the grade is bad, the SAT is bad, and the letter is also bad? What is the probability of this happening, all this happening? You just plug in these values. You just plug in these values here. You take P, D0, P I0, Pg0 given I0 T0, P S0 given I0, P I0 given G0. Note that each of these values are already there in the CPTs. What is PD0? PD0 is this. What is PI0 is this. What is Pg0 given I0 D0? Oh, it should be G1, not G0. It should be G1. There is no G0. This. What is PS0 given I0? Is this. What is PI0 given G0? Oh, G1, not G0. This. Sorry, PL0 given G0 is this. Okay, so all these values that we need for any of these rows, for computing any of these rows, are already there in the CPT. So together with these CPT values and the factorization obtained from the graph, I can reconstruct back the full joint probability table. And once I find out the full joint probability table, I can find out any other probability from this table. For example, if I want to find any marginal P, D0, I0, what I do, I'll mark out the rows containing D0, I0 and add up their probability values. Only for the rows which contain D0 and I0. Okay, and from the definition of conditional probability, I can also find conditional. So everything that I want, I can find out. So this is a complete representation. This is a 100% correct representation. So what is the advantage of this representation? advantage is if you are to, so you might, instead of all this graph and CPTs, you might as well store the full joint distribution table. But that would take a large number of entries. The storage would be very high. It's like, it will take how much? 2 to the power 4 into 3. So many entries. So 2 to the power 4 into 3 is 16 times 3 is 48. Whereas here you see, you need much less number of storage. You need 1, 2, 3, 4. And this is 3 times 4, 12. 12 plus 4, 16. 16 plus 6, 22. 22 plus 4, 26. Whereas this would require 48. So this table will have 48 rows. Whereas here I have only 28 values in the tables. Okay, so it is a more compact representation. It is a much more compact representation. So that's the main benefit. And you can reconstruct back the full table anytime you want from this compact representation by applying this factorization rule. So now, so this is about representation. Now let us see if there are any long-range dependencies, long-range influences, not dependencies, influences that are there. And that is concretized in terms of something called an conditional independence. So normal independence, you know, normal independence is two variables x and y are independent if the joint probability is product of their marginal probability. Is the product of their marginal probabilities. So then we write this notation: x is independent of y. And now we have an additional notion that x is independent of y given v, conditioned on v, if the following holds, that x is independent of y given v, if pxy given v is px given v times pyb. So the same thing, same structure, pxy given v is factorizes into px given v and py given v. Okay, so then we called x is conditionally independent of y given v. Okay, and this need not be a single variable. This can be true for where x is a set of variables, y is a set of variables, and v is a set of variables. And the marginal independence is a particular case of this conditional independence. We call it as given nothing. X is independent of y given nothing. Here are some examples. So the overall you can think of it's that so x is independent of y means information or observation of x doesn't tell me anything about observation of y. Say you are taking two unbiased coins, or say two biased coins. So looking at the outcome of the toss of the first coin doesn't give you any information about the biasness or something about the other coin, or the outcome of the other coin tosses. These two are completely independent. And conditionally independent means, so the x doesn't carry any information about y. But for example, let's take this. Let's take these two are the coin tosses which can take on value 0 or 1. And let's say I have another variable v which is equal to OR of 0 and 1. So these are binary variables, OR of 0 and 1. Let's take this setting. So in general, observing y doesn't give any information about x. But suppose I observe v, the OR of x and y, then I have some information. Observing y would give me y depends on x now. So it's like this. So if x and y are independent given v, that means in general, y gives you some information about x. They are not independent. Why? If they are independent, y would give no information about x. So y gives some information about x, but v supersedes that, in the sense that once you have observed v, you have all information about x that y could have given. Y doesn't give any additional information. Let's take the case. Say it's it's July, and so that's one variable, the month of the year, and x is whether it's raining outside. So in general, the month has an influence. They are not independent. They are not independent that which month it is and is it raining outside. X and Y, they are not independent in general. So looking at one, you do have some information about the other. But suppose you have really gone out and see that people are wet. Somebody has come in and he's wet. So now this information already tells you it's raining outside or not. You don't. The fact that it is July doesn't give you any additional information beyond this. So in this case, the July and raining is independent of each other, given somebody is wet who has come. So here are some examples. In general, the type of a car, sports car or something, does have an influence on whether you give a speed fine or not. In general, they are not independent, but moment you note the speed of a car, it doesn't matter what type of car it is. It doesn't give you any additional information. Okay. So these are some examples you can see. Say, for example, position and velocity at time t plus 1 is naturally dependent on the position and velocity at time t minus 1. But moment you know the position and velocity at t and the acceleration, then t minus 1 doesn't give you any additional information. You can have all the information from t and acceleration at t. Okay, so these are some examples, and this actually captures the notion of influence that we talked about. The notion of influence as we talked about. As I have said that let's look at some influences. Definitely grade is influenced by difficulty. Grade is influenced by intelligence. Letter is directly influenced by grade, but also indirectly influenced by difficulty. So this kind of influences can be written down by a set of conditional independences that we described. So let's and in fact, since this is the expression for conditional independence I already talked about. Sorry, you can find this out because that's also a factorization. You can infer this from the factorization of the graph. Okay. Say here I find these are the independent. So D is independent of Y, S is independent of D and G given I, L is independent of I, D and S given G. These are the if we just compare this factorization and this factorization, you will come up with these independences. So since independence has also factorization, to identify conditional independences, you just look at the factorization of the graph. You look at the such pairs, that is PD given I is PD into PI. So such things you identify, and that will produce your conditional independences that exist in this graph, and that will in turn give the influences. But since this is a directed acyclic graph and there is a particular structure, some conditional independences can be proved. Example, this is always true in a given graph. So note that there are many conditional independences given a graph, given a factorization, and you can identify them. You can just examine this thing, and you can extract such conditional independences, And if you have extracted this conditional independences, they give you an influence of directed, what influence what. So this is not so evident in this case, but if you really take a big network with a lot of variables, say you are trying to understand what gene affects what other gene, and you find out such indirect influences, such flows of influences, and you find out some genes which are completely independent, they do not influence each other. And so thus conditional independences are important. They are important for understanding the underlying structure. So you can extract a lot of such influences. The advantage of this graphical model is that you can systematically do them. You can not just by this trial and error or by examination, you can do this. You can systematically do them by applying some algorithm. I'll start with the first such rule. Rules of conditional independences. The rule 1. A node is conditionally independent of its non-descendants given its parents. So that means a node X is conditionally independent of non-descendants of X given parents of X. Okay, so let's take an example here. Let's take the variable grade, and SAT is a non-descendant. So grade is independent of SAT given the parents, which is difficulty and intelligence. Difficulty and intelligence. Okay, so this is always true. In any base net, this always holds. And this gives you. But there are, so this is kind of a local intelligence structure. You need the parent and then this thing. There are even more longer range independences that holds true. We'll try to look at some of them. Okay, so let us look at some of this. Let's take 3 variables. Let's look at particular structure. Let's look at variables A, B, and C. Suppose there is this, and I'll write down this thing. So if I look at independence properties that come given a particular structure. So ABC 3 variables, there is only a small triangle light up structure. We'll examine them. Let's say there is this structure. There is a edge from A to B. This definitely means that A influences B. You cannot write A is independent of B. Cannot write. They are, rather A influences B. And the other way around also. Other way around also. Okay. So there is a influence, or rather instead of independence, let me write it down as influence, which is the reverse of independence. Okay, so these 2 holds, this holds. What about this? What about the independent structure? This is sometimes called a causal flow. Causal flow. Okay, so this is also sometimes called a cascade structure. Also sometimes called a cascade structure. So what can I tell? So naturally, I'm talking of 3 variables. So let me talk of conditional independences rather than just independences. Or in another way, I can think of, does A influence C? We'll see that if you have observed B, That's you remember the plate diagrams. I have shaded this, so this B is observed. B is observed. B is observed. Okay. As it turns out that since B is a more of a direct influence, if this kind of structure holds and B is observed, that means this kind of structure holds, then A is independent of C given B. A is independent of C given B. All right. What about this structure, common parent? That means there is a structure like this, A, B, C. This kind of structure. This is rather a evidential structure. Okay, B causes A and C, and I have observed B. Sorry. I have observed B. So in this case, also it turns out that A is independent of C given B. You don't get any additional information about A by looking at C if you have already seen B. So this holds, this holds. In fact, this you can prove also. You can easily prove this. So let's take this structure. You can easily prove this because if this structure is there, this is the factorization, and if this is the factorization, you can easily get this. So you can prove this. For the cascade case also, if you just write down, very simple, just write down the factorization and try to derive this. You can derive this. This is the definition of conditional independence. Okay, there is a third structure which is like this. That means A causes B, B also causes, sorry, A causes C, B also causes C, and I have observed C. Now, does looking at A gives information about B? Let's look at this. Okay, let's look at this. So difficulty influences grade of a course. Intelligence also influences grade. But suppose suppose I have observed grade to be say A. So now are difficulty and intelligence independent? If I have not observed, maybe difficulty and intelligence are related, because if I see intelligence and I don't know what grade is, I have some notion about how difficult was the course. Okay, but once I have observed the grade, then these two are independent. Then these two are independent. Sorry, the other way around. I think I made a mistake. It's other way around. So if I have not observed the grade, so it's the other way around here. Here, observing this made them independent. Here, observing in the V structure, observing C will make them dependent rather than independent. That's what we can see from here. Suppose I have observed that the grade is A. Now probably I know that if I know the person is intelligent and the grade is A, or rather put it like this, if I know the person, and definitely the course should have been easy. Definitely the course should have been easy. Okay. So now I have some coupling between these two. So this type of structure is known as a explaining array. If you have C, I have explained array. I have already some explanation about A from B. Okay. And note that this is the V structure is the reverse of the earlier two. B made A and C independent. Here observing C made them dependent. Not observing them would keep them independent. Okay. So now using this kind of local structure, let me try to find out some global independences. I'll explain it this way by some property known as deseparation. So we'll say that a set of variables is deseparated from another set of variables given a third set of variables C if so A, B, we look at this kind of graph property is deseparated, D for directed, deseparated from E and D given C. Given C. It's kind of a graph separation kind of thing. Then we would call it deseparated. I'll give an example what deseparated means. If we can find such deseparations, then we can say AB, then we can say A comma B is independent of E comma D given C. Note that C could also have been a set. All right, so these two are equivalent. If you can find this kind of graph properties, you can establish this kind of conditional independence properties. Establish this kind of conditional independent properties. Now let's see how do I establish these graph properties. I look at this way. So if I have two variables A and C, let's first look at three variables A, C, and E. I would consider an undirected path. Forget about the directions of the arrows. I'll consider an undirected path from A to E, going through other nodes. I would call this a trail. I would call this a trail. Okay, and I would call this an active trail. Okay, I'd call this an active trail if the following happens. So let me put it this way. Or okay, I think this is dying. So if you look at a trail and you look at any intermediate node in the trail. So this is a trail. I'll call this active in the following case. For any intermediate node in the trail, if it is not a V structure and it is observed already, then this trail is blocked. So for example, this is not a V structure. This is not a V structure and C is observed, then this trail is blocked. Okay, then this trail is blocked. On the other hand, if it is a V structure, and this is the definition. So if we have a non-V structure, which is either this cascade or this evidential, and W is observed, then it is blocked. Then that particular trail is blocked. And if it is a V structure and the W or not any of his descendants are observed, that is in V, then also it is a blocked. It is a block structure if you have not observed it. For example, let's take here. This is a V structure. If we look at this path from difficulty to intelligence, if you have not observed grade or letter, then this is blocked. Then this is blocked. This is blocked. But moment you observe either grade or its descendant letter, then it becomes unblocked. This block is removed. It becomes unblocked. Moment you observe it, it becomes unlocked. Okay, so there is two different cases. If there is a V structure, then as long as anybody in the V or its descendant is not observed, they are blocked. They are not yet open. You observe them, they get open. This is for the V structure. If it is not a V structure, if you have not observed it, it is open. The moment you observed it, it gets blocked. You can think of this as valves, which open. One valve opens when they are observed, another valve opens when they are not observed. And so the cascade and the other structure and that child structure, whenever you observe it, it closes. As long as it is not observed, it's open. And for the V structure, it's the other way around, and also for its descendants. Okay, so this is when we call a trail to be blocked, if in any two of these conditions. And if a trail is not blocked, it's called active. And this would be this and this would be deseparated given C if all trails from this to this, or sorry, the other way around, there is or okay, let's put it this way, all trails from this to this are blocked. All trails from this to this are blocked. Then you would say them to be deseparated. There is no active trail between AB and ED. Every trail is blocked. Then you would say that AB and ED are deseparated given C. And once we know that they are deseparated, we can find out, we can infer this conditional independence. Okay, so this is the definition. If you remember this definition, it's easy to remember. The earlier thing, the parents are independent of its non-descendant, is a consequence. It can be shown as a special case of this. Also, you have another thing is that if you look at a particular node X, you form something called a Markov blanket. Markov blanket of X. You also call it a Markov blanket of X. Consists of parents of X, children of X, and parents of children of X. So the Markov blanket for this would be, for grade, would be this, this, and this. This would be the Markov boundary or the Markov blanket. As a corollary of the deseparation, you can get a node X is independent of every other node in the network given its Markov blanket. So Markov blanket kind of insulates it from everything else in the network. Okay, so this is the definition of deseparation, and deseparation helps you find out all conditional independences by applying this graph property. Actually, it turns out there are even more other conditional independences beyond the deseparations also, but they are more computationally difficult to find out. It's difficult to find out some graph algorithm. Okay, so finally, let us formalize this. Given a graph, directed acyclic graph G, IG is the set of all conditional independences that you can extract from that are implied by this graph. Okay, so that's IG. All conditional independences by deseparation, Markov blanket, whatever, everything you find out, you collect them. Actually, beyond deseparation also, everything that holds true. And let's say, given a particular joint distribution and all possible factorizations of the joint distribution, you can also induce a set of conditional independences, and let's call that as IP. So G would be called an IMAP of P, because see, G, I have said that G is a factorization, and the factorization is for a particular a distribution may have multiple factorization. So the question is this a correct one? So we'd say a graph G, a DAG G, is an IMAP for a distribution P if the set of independences obtained from the graph is a subset of the set of independences that may possibly hold true. That may possibly hold true. If this condition holds, that means this is the graph is a subset. It doesn't have any spurious or extraneous independences inferred. Then it's called the IMAP of the probability distribution. Connected DAG is an IMAP for any distribution that we have already seen. A IMAP is a minimal IMAP if removal of a single edge from the graph doesn't preserve the IMAP property. Okay, a distribution may have similar multiple minimal IMAPs. A map is a perfect map if Ig is equal to Ip. So it not only finds the subset, it finds exactly the set of dependencies. Then it's called a perfect map. So we would like to, moment you give a graph, we have to show that it is indeed an IMAP. Okay, so I stop here. Today I stop here. And in the next class, we will go into undirected map. So what we have covered today is kind of just the representation. How do you represent a joint probability distribution using a directed acyclic graph? Next, we'll move into how to represent them using undirected acyclic graphs. And then we'll move into inference, and then we'll move into learning. So what I'll do next class, I'll cover as much as possible. The 2 classes that I have missed, that I'll upload the recordings. You please go through them.